Welcome, welcome, welcome to the UpKeep Pledge Pros Podcast, a podcast dedicated to UpKeep's customers and the community through our new ambassador program. UpKeep is unmatched value and unwavering support. We are absolutely out there crushing it. Today, we have a very, 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 very special guest. He is my friend, a salty sea dog, a dude who knows it and knows what's going on in the industry, a bona fide, as Greg Christensen would say, expert, doctor of motors and electricity, Howard Penrose, the MotorDoc. Howard, welcome.
Hey, thanks for having me.
You are very welcome. I am super stoked. Howard and I have talked in the past. We talked to SMRP. We've been on podcasts together. We are kindred spirits. He's a fellow sailor just like me. I'm going to try to keep this podcast in time. Howard was a little concerned we may go over. But Howard is the founder of Empath LLC and MotorDoc.
MotorDoc.
MotorDoc. Yeah. Okay. Founder of MotorDoc, who utilizes the Empath, right? Yeah. So Howard is going to teach us some things about Empath because it is a very, very, very real condition monitoring tool. And Howard is the sought after expert in this field. So I will let him say those things. But before we get to that, Howard, tell us who you are and ultimately MotorDoc.
Okay, well, I'm Howard Penrose. I go by I've gone by the nickname MotorDoc since the Navy. We talked about that, right? On the Roosevelt, captain named me the MotorDoc. So later on, I figured might as well get a PhD. And of course, I don't like calculus. So I went industrial engineering, which meant I got to enjoy probabilities and statistics, which I wish I'd gone the other direction now, but that's besides the point. It also means that I worked within that industry and actually taught at UIC for a period of time and ran the Energy Resources Center there. But during that period of time, I was dealing with all the stuff that we now call machine learning, AI, all the other stuff. We called it VRML back then. I don't know what the latest name is. So that's,
it changes daily.
Yeah. So I've been in motor repair. I've been in academia. I've been a consultant. I've, all kinds of stuff. Most people know me for electric machines, but we do a lot of electrical reliability, mechanical reliability, focusing strictly on commercial and industrial applications, including utilities. So for instance, I chair standards for wind with the American Clean Power. I sit on all the standards committees for most of the standards that we use for testing electric machines, insulation systems, and the like. And a bunch of other stuff as a volunteer, even former SMRP chair. So I'm going to keep it at that. Most people know who I am. If you want to know more, LinkedIn. Just look up my name or MotorDoc on LinkedIn. The company itself, we've evolved. We first started as a reliability consulting firm under the name Success by Design. And my clients were like General Motors Corporate. We were responsible for all facilities for developing energy and maintenance programs. As part of the quality network plan maintenance, we did Amtrak, US Steel, and several others. So around 2009, when the economy had fun, that all went away. Went back
that's when I joined the service.
Yeah, went back to work for Drysilker, and then got out of there in 2015. March 31st, literally shook the hand of a customer. I was down in St. Louis doing a field service project, shook the hand of the customer, and he says, "Why aren't you going to stick around for the meeting?" I go, "I don't work for Drysilker anymore," and left.
Nice.
Right at 3:30. So, and then the next day, I had kept Success by Design in operation as a publishing house, primarily for reliability, maintenance, and sports. And then changed the name in May to my nickname, MotorDoc. So, and also altered things a little bit. So a lot more field service work, Like I go out and I do what I really enjoy doing, which is troubleshooting.
Me too.
Exactly. Yeah. I mean, I get the calls when people have been struggling with stuff for months and haven't been able to figure it out. I mean, that's what let's just say it's from a lot of experience having to do that. Right.
Right.
So if something goes wrong, nobody can figure it out. We get a call. So, and we do our best. We only talk about the ones that we're successful at, which is most. Yeah, so and a lot of travel. I mean,
oh yeah.
I've been in town this week, and that's because I was supposed to be an expert witness at a court case in Denver, and unfortunately, fortunately, really, won the case without having to go. So
that's the best case scenario.
Yeah, exactly. Based on our position on that case. And the other side's position, which was horrible, but that's something we can talk about another time.
Yeah.
Yeah, so a lot of troubleshooting, vibration, motion amplification, all the offline testing. We use Electrum and All Test and whatever's available. Most people don't know. I also, when I'm in the field, if a customer has PDMA, we'll use their PDMA device and so on. I get exposed to a lot of technology, everything from the low voltage to the high voltage stuff. And that's part of the reason I sit on the standards committees. So we do, the primary focus though was, and I started working on this in the 1990s, was a focus in an area called electrical signature analysis. And that's where the empath comes in. Now, you mentioned that I'm not the founder of empath.
No, yeah, sorry, I mixed that up. I see empath so much, and I'm very interested in it. It was just like, oh, empath, like
yeah. So empath itself is a Framatome. It used to be a Riva Framatome product. They're a large 30,000 engineer, $12 billion nuclear services company. It's built in Virginia at their parts center for us, and we're the exclusive distributors. So that's because they had needed somebody to roll it out to industry, and so we do a lot with it, actually, quite a lot. It was originally developed. As a matter of fact, it is in a direct line back to Oak Ridge National Labs, where a gentleman by the name of Howard Penrose and his team developed the first electrical signature analysis. They used to call it motor current signature analysis, but it's basically the same thing. And it was developed to look at bearings and gears in motor operated valves. Everybody kept saying something about rotors and stuff like that. And I accidentally fell into that group briefly until after a discussion with Howard Penrose. He goes, have you looked at the patent? I go, no. So I took a look at the patent, and one sentence mentions the word rotors. Everything else is about fans and belts and all the stuff that we go in and evaluate. The other nice thing that it does is a direct result of taking in both voltage and current. So I've got power quality, I've got the motor, I've got the driven equipment. It sees everything at once. So I'll go into problem cases, such as we had to help get Buckingham Fountain back up and running, and the big fountain down in Chicago. You know what I mean? They had used vibration. They had used other tools and everything else. We were able to, in about 20, 30 minutes, figure out what was wrong, so they could repair it, because that gave us just an extra angle. So we had a full view of everything.
Sure.
In the wind industry, it's played an even bigger role, because once we had developed the methodology to do it, which I had done in 2003, people have only became really aware of it in 2013 through 15 for generator and gearbox and main bearing testing. But it wasn't until one of the primary failures for the generators, which always went without detection before. Nobody, unless you went up and physically looked at it and saw the defect, which would always end up as a catastrophic generator failure.
Right.
Well, our testing technology allowed us to walk into the base of a tower without having to climb, take data, and right then and there know the condition of the rotor connections.
Right.
And that meant that it was a $10,000 roughly repair versus $180,000 to $200,000 repair.
Right.
And the outage time is a half a day versus weeks.
Yeah. Right.
So it really started gaining ground there. And then all of a sudden industry started to pay more notice to the technology, and we haven't slowed down since.
That is very clear. You are a tough guy to drill down.
Yeah.
Howard is a shaker and a mover. Fortunately, his wonderful wife is there to assist him and keep him straight, right?
Yep. You mean the lady who lives in the house that
Yeah.
Every time I come back, who are you? I don't know. Who are you?
Haven't seen you in a week. So I wanted to ask you, you're talking about electrical signature analysis, and it being a full picture, right? And I'm a huge fan of you and what you do and just electrical things in general. But it's so accurate, right? And it gives you such a strong look into the failure mechanisms. And is that because, since you're monitoring current and voltage simultaneously, you're able to pick up on very minute changes in those two parameters, right? That ultimately correspond to some form of internal problem, mechanical looseness, overload, wrong frequency, or soft foot,
worn or damaged gears, failing bearings, lubrication issues.
Right.
My favorite is hearing companies say that they have the earliest detection. Well, I'm sorry, but I'm watching watts change.
Right.
So that's one of the keys to the technology is the transducer is the magnetic field.
Yep.
So it's not the rotor, it's not the stator, it's a magnetic field, and a small change translates into something bigger. Well, part of what we do is we convert everything over to watts. Right?
Volts times amps.
Calculation, right? A little more complicated than that, but that's the idea. Well, what basically what that means is every defect or potential defect shows up as a loss.
Right.
In the system, starting out with a watts and then kilowatts.
Right.
Depending on the size of the machine. We use it as a relative measurement. So I do a comparison between the full output, input versus output watts, which is your efficiency. And then I do a comparison of those watts to a percentage. And that's how we determine how quickly something is moving along. So my trending is actually watts.
Right.
We talk in terms of fault detection in current signature and voltage signature, the actual spectral analysis. But for condition and how quickly everything, and that's what I think blows more people away, is I'm able to turn around and say, well, you've got this much time left because you're at this percentage of total watts on that defect. And oh, by the way, it's costing you this much a year, which is going to get progressively worse. And I have a direct tie from that to emissions.
Right.
I mean, so it's actually direct measurements, not implied.
Right. And you're not using buzzwords to try to get people all hyped up around what it's doing. You're doing the real work and showing the real value.
Oh, it's an expert system, right? And we built in all the algorithms. I'm working with the programmer on the latest stuff. We went back and we've had a few more corrections I wanted in there for earlier fault detection. Through an Electric Power Research Institute study that happened over the pandemic, it was also determined we had the least false positives.
It's amazing.
Negatives. I mean, we were detecting everything. Everybody was compared to it.
I love it.
Yeah. And all the other stuff, including some of the new kinds of technologies that are out there, didn't perform as well.
Yeah, they normally don't. It's a lot of hype, a lot of buzzwords, a lot of silver bullets.
Yes and no. I mean, they're good for anomaly detection.
Sure.
For instance, I use I use cloud for any of the stuff we're monitoring, like incoming power,
Sure.
because that was actually Onyx Energy, the owner there, Chris Lopalato, who's been calling me like crazy while we're talking.
We're busy, Chris.
Yeah, we're busy. He one day we're on a call and he goes, "Hey, have you ever thought of using it for power monitoring?" I go, "It's probably a little expensive for that." And then found out that the power monitoring companies for the type of power monitoring that we're doing are 4 or 5 times our cost. And it's like, oh, okay, let's do it. And
you don't know what you don't know,
No. So then I took that and we take the data and we toss it up to AWS. So it's an edge system. So all the actual work is done on a local small industrial PC, toss it up to AWS. And then I use the anomaly detection there.
Right.
So I'm not having to stare at.
I love that you keep using the word detection.
Yeah. Yeah.
And not prediction.
Yeah. Well, I'm actually working on an article right now on predictive maintenance, and with all the new machine learning and AI, the 2 main studies that came out both say more than 75% of those implementations for predictive maintenance fail outright. They're just mostly wrong. And suggested a different direction for that.
Sure.
And I agree. I mean, I'm a data scientist.
Yes.
I've always been a data scientist. Well, now the term data science came about in 2015, right? But as by default, as an industrial engineer, I take in data and I use it to model things. That's what I used to teach even.
Yep.
And that by definition, data scientist. So
your implementation failure, I mean, that's everywhere, right? I mean, implementation is the key.
Yeah, usually on the pilot or stage 1.
Always. It's because, and I find that you have to know a decent bit about what you're after.
Yes.
Before you even do anything.
Well, you have to know the technology that you're measuring.
Sure.
And textbooks don't work.
That's right. Everything has to be.
Systems I run into, it's some student who sat down at a kitchen table and came up with something, and then poof, there it is, right?
Yes.
Sorry, I didn't mean to interrupt.
No, it's okay. You're right. I mean, like there's so much discovery and business alignment and understanding legwork that needs to happen before an implementation takes place.
Yep.
But that requires a lot of knowledge and a lot of work.
Yes.
And it's so much easier to make a cookie cutter implementation and go, just spray this out there. And that's what we're doing.
Yeah.
And what I love about you and Empath is that there is no spray of things. It's no, we will assess, and we will accurately detail the failure mechanisms or failure modes that are plaguing you. We're not going to go, oh, well, let me hook up this and see and blah, blah. It's like, no, this is the approach, and this is what we're after. Yeah.
My favorite part is it used to be just because I'm one of those people that's obsessed with a particular industry, like electric machines, right? They're everywhere.
They're everywhere.
But it used to be, we'd love to get your brain in a box. Okay, great. So we did it. We've been putting all the analysis, all the capabilities into
whoever that is, we're busy.
Yeah, into the technology so that it's automatically detecting. It's an expert system, right?
Sure.
So it automatically detects things and will show you why. I mean, it automatically pops up the lines and everything else. And so now people are saying, oh, well, the problem is you need to have a PhD to understand the data. No, you don't. The PhD has already put the stuff in the box. The box does the work. I mean, that's
literally.
I don't have a dozen people here doing tech support with all the systems we have in the field. All the systems we have in the field. There's a handful of people over at Framatome, and there's me. Right, doing tech support. So if somebody calls up and they're having a problem with their system, they're talking to me. And if they can't get a hold of me, we've got backup. But The reason we can do that is because the system is built for that. It's built to not require continuous phone calls. It also means we don't have to charge annual fees.
Love it.
I don't have to have a staff literally only 25 or 30% billable, basically, to do support. So the end result is I spend, tomorrow I'm going to spend a half an hour doing tech support for 2 wind sites to gather data that we need for a research project for the Department of Energy and several OEMs, right? And when that's all done, I take that and I plop it into a model that I built before, and then we turn around because we already know the problem. This is all the proof side of it, and then we do a paper in February.
Sure.
And then everything gets resolved, and the world's
yeah, it's all better. Everything's fixed.
That's what we do.
Everything's fixed.
But anyways, but we're not losing time on the tech support side. We spend the time doing the programming, testing, making some mistakes. I mean, trust me, there's been a few. But they're easily recovered. So by keeping everything small, Framatome is this massive organization. It's a global organization. They have a small, tight team that works directly with us, and between the 2 companies, we get all this stuff going, and then I gather feedback from global distribution and everything else, as do they, and then we sit down. Like this Friday, we'll sit down for our 60 to 90 minute call, discussing all of our findings and discussing next steps forward.
Yeah.
Right. So
it's a constant feedback loop, right?
Exactly. And then I got the software 2 days ago to evaluate the latest version, which will probably be 9.0. It blew my mind. And then I said,
yours blew your mind?
It blew my mind. Well, I couldn't believe he actually got it all in there. And then there's the next phase that we've been working on. I've been teaching, I've got in my books, the direct relationship by defect. So listing defects, energy consumption, and the emissions associated with that specific defect. That's all going to be built in.
That's awesome, man. And it's so cool to think that, thinking about an electric motor.
Yeah.
Any applied stress to that motor, you're going to see a change in its field.
Oh, yeah.
In its current. It doesn't matter if it's the most minute change. There has to be a consumption of energy somewhere, whether in the form of heat, which is current, right? Yeah. Or RPM or load or something. And the fact that you're able to tap into those things and see them at such an accurate scale is so cool to me. Like when you said you're literally monitoring the magnetic field between the rotor and the stator.
Mm-hmm. Yep, that's my transducer.
So awesome.
Yeah.
The next step here is I want to see it.
That invite for the week after next is still there.
I know. We got to talk about that.
Yeah.
But so I want to jump to wind for just a second.
Yeah, sure. It's a popular topic.
It is.
We do wind, we do solar, energy storage stuff, primarily transformers for those and the drives.
So when I worked on the waterfront, part of the company I worked for's job is we would literally unload windmill parts. Mm-hmm. And then they'd at Bethlehem Steel, actually. It's not Bethlehem Steel, but it's Trade Point Atlantic now. But I always wondered when you're monitoring these windmills, I believe you told me, correct me if I'm wrong, you don't even have to climb up the thing.
No, as long as the transformer's down tower, or there's CTs down to or there's something directly between the generator and the first transformer that comes down to the base of the tower. Got it.
And sorry, go ahead.
No, go ahead.
So are there any electrical devices? I'm asking this because of what you just said. Are there any particular electrical devices that can mess up what you're trying to do if you tap into a certain spot that may not be correct?
No, I mean, the most that'll happen is if we connect into something that's connected to to a VFD in the tower, I just have a little extra noise. But
Gotcha.
When an expert system looks right past the noise anyways, a machine learning system cannot.
Gotcha.
So anybody who has attempted the machine learning systems on towers have failed miserably. And there's a lot of reasons why. Part of it is that by definition, the way that a tower works, it is multiple different configurations based on wind speed. Right. So it operates completely because it has to do VAR correction, which means voltage regulation for the grid. The ones I work on are the grid-based systems or the big power systems. It has to be able to do other compensation as goes through. So basically, when we see when we're monitoring a tower, there's things that we do. And it's now in the software. It used to take me a half an hour to 45 minutes a tower to analyze. Now it's a minute. Well, it's built into the software now. I go in and I just verify what the software is doing. Somebody asks me to do something, I look deeper into the results on every test, only because if I find areas where we're missing things, I need to go back and see why and then have it corrected, right?
Confirmation is important, man. There's no
But
problem.
our average user, I mean, they start using it, and I just got a text from one of the guys. I haven't heard from him in months, and I texted him back and I said, have you put the machine to one side and you're not doing anything? Because we used to chat all the time. And he comes back and goes, no, we've just been so busy with it. It does all the work.
Yeah.
We hook it up. It tells us what's wrong. But from the tower perspective, for our specific technology, no, that it doesn't matter as long as I'm getting a direct path to voltage and a direct path to current.
Awesome.
Once it converts it up to high voltage, now I'm talking about, so it'll go through and it'll come down tower usually at 480, 575, 690, or 1,000 volts. Normal, the default is usually 690. There are some towers that are 12.4 kV and a smaller subset that are 13.8. So those are very, very small groups. And then there's a new one that's 6 kV, and they do that to reduce the weight of the generator and increase the size. Like a couple of weeks, 3 weeks ago now, I was at a GE in Schenectady. I can talk about it now because they just publicly announced it. Looking at the 6 megawatt tower, which will be the largest land-based in North America, well, in the United States. There's 7 megawatts in Northern Canada that were built that never ran. Yeah, it was an experiment by some company. It's out in the middle of nowhere. But they tried to run, but they were just a maintenance nightmare. GE is not going to do that. It was kind of funny because when we were there, I go, what are those, the 2.6s? Because that was the last release they had. They make up, the GE towers, 1.5s and 1.6. When I say that, it's megawatts, by the way, per tower. Those make up 52% of the total population of 74,300 and some. I didn't look today. But it's been going up at a pretty good clip. Finally, I mean, we were 2/3 down from the number of towers that were supposed to be built because then the present government point is to make red tape unbelievable. So it's and in other cases, turbines that are just sitting there because they don't have power lines to them, so they need distribution to get to them.
Infrastructure problems,
big time. That's where we've got input into National Grid, things like that. The programs there. And that's a direct result of the work I was doing at SMRP.
Yeah, I love that.
Yeah.
So one other question: when you're taking into when you're monitoring these assets, motors, generators, things like that, do you? You talked about efficiency for a second. Do you have to take into account the inherent motor or generator's efficiency numbers in order to get accurate data, or you don't need to take that into consideration?
When possible. I mean, the closer you can get to what on the nameplate, the closer you'll get, right? Because it'll set a baseline. It looks at the actual input and output, so it'll produce an actual efficiency based on that. But then it compares it to a set of curves.
Gotcha.
Methodology also came from Oak Ridge National Labs, and that's the Ormel 96 methodology. So Ormel 96 was a method of calculating efficiency that in studies comparing the efficiency from machines like the Empath. And I think the Baker Explorer had a similar result, right? I don't remember if PDMA did. I know that they were working, they had something similar as well. But I don't remember, I haven't spent a lot of time on what calculation they're using, but the other two, so I don't want to, give them a poor.
Yeah, no, it's all good.
There's three expert systems in the industry, right? There's us, and actually Alltest is Empath. It's Empath Junior. It doesn't do all the same things that we do. But it's the same thing. I developed it back in 2003.
Nice.
Right? So, and then you've got the Baker Explorer and the PDMA. PDMA actually came third in the EPRI study. So when us, Alltest, PDMA, and then Baker, and then everybody else was a distant fifth. But so those four are the expert systems that are out there.
So would you say then that when the Empath system is calculating an efficiency rating,
yeah,
technically we would call that a true efficiency, right?
Within 1% to 2%, depending on the load. Yeah. So it's based on it's accurate to within a percentage, 1% of the 1 point, basically, of the actual efficiency.
Right.
So if they were to put it on a test bench, an accredited test bench, and test the motor at using IEEE 112 method B, which is the legal requirement, by the way, right? In Canada, CSA 390, which is basically the same thing. There's actually, the Energy Act actually calls for that test. If they were put it there and they got, say, 94%, and we were to test it, we would either show it in a range from 93 to 95. So it tends to be a lot closer than that, but that's the tolerance for doing the type of testing we do at that point. Now, that also includes all of the nastiness in the operating environment. So on the test bench, they'll get 94, and we're in the field with all the impedance differences and all the other stuff going on, and voltage unbalance and this and that and the other thing. We'll read the actual operating efficiency.
And
efficiency.
That's what I was going to say. And the cool thing about that is that's contextual efficiency. Well, that is legitimately application efficiency of what you're doing, right?
Well, yeah. And we actually had an instance this year where we went in, and a company, one of our customers, we were the subcontractor. We went in and we were doing just testing. And they said, oh, by the way, this particular machine right here, this is this new type of machine, and it's 99% efficient at 100 horsepower. And I go, there is no such thing as 99% efficient at 100 horsepower. Oh, it had a 0.99 power factor because of how it was designed with capacitors built into the winding. And they said, oh, and it has a generator winding, so it actually generates power back into the system. So it was a perpetual motion machine, the way it was described. So we went in and we tested it. And then we tested a motor that had been rewound 3 times in the exact same, it was actually in the same pump loop. So barring any changes, we went off of the percentage load, right, based on the actual kilowatts and the current. So we did a comparison there, and we said, so they were operating, this one was operating 103% load, and the original was operating at 98% load. Well, that difference for the exact same basic load was because they were actually less efficient than the motor that was rewound 3 times by 3 percentage points. They
Wow.
actually fell under the legal requirement for what they had on the nameplate.
That's crazy.
And they brought in their bigwigs. They brought in 6 PhDs of engineering. They brought in their CEO.
We got one MotorDoc
screaming across at me. Yeah, this isn't the first time. I kind of enjoy those situations.
I love it.
Don't ask me why. I've had some big companies put a lot of people across from me, and what was that old meme? It was the meme of the Hulk wearing a pair of glasses, and he says, don't get me angry because I back up all my stuff with fact.
Facts are tough, man. People don't like those.
And in effect, they tried to, and I said, great. Then I contacted Advanced Energy, which was a certified laboratory, and I said, I will pay for that motor to be tested. As a third party, I will pay for them to have that test done, and everybody involved can have a copy of the test results from there. They don't have to come through me. One's going to go to the OEM, one's going to go to the customer, one's going to go to my customer, and one's going to come to me, the end results. And anybody who needs to stand there and watch can be there. Guess what hasn't happened? So it ended that whole era. And what was worse was because how it was built, the harmonics going into the system were huge. It had an air gap harmonic, because basically what they did is they used a feature we watch out for. I'm a certified, and I'm a journeyman rewinder, military trained journeyman rewinder, right? And there's something called a chord factor, and it's exactly what it sounds like. It's a harmonic. And you cannot have the chord factor be a 1.0, meaning that you will have an oscillation, you'll have actual voltage and current harmonic going back into the system. The motor will cog, all kinds of other wild things that occur. Those were being sold as a feature. It's like, oh, the reason it operates like that is because it's generating power.
Oh my goodness. Oh my goodness.
So I'm not going to mention who it was. I took down my original post on it. That was part of the agreement to get them to sit down quietly at the table. I put it up there to get them to the table.
Right.
They learned very quickly that I'm actually a registered journalist. So, with the National Writers Union. So it's like,
I'll put it out there.
Yep. If I write something, I'm a journalist. Sorry.
So, Howard, I have one last question for you.
Okay.
In your opinion,
yeah,
what do you think the biggest misconception about electric motors is? Just in general, any application, what is the biggest thing that people genuinely don't understand about electric motors?
Where do I start?
The biggest one. Just think of
there's not a biggest. It's actually, let's talk about systems. So I think the most dangerous one, because we ran into this in Wind, an OEM came out and told everybody, because the bases are semi-flexible up tower in the nacelle, you don't have to align the machines.
Right. Now,
mind you, all the repair shops loved it.
Right.
A lot of bearing replacements. So I'd say one of my pet peeves on the mechanical side is that people perceive that if they get a coupling, that the coupling manufacturer says it can withstand 10 thousandths misalignment or something like that, that somehow translates to the motor and the driven equipment. Absolutely false.
Yeah.
Absolutely false.
That's applied stress.
Yeah, you're talking. There's physics involved, so it's misaligned, and the coupling will survive the energy loss across it.
Sure,
there's an energy loss across. We see it.
But where's the energy go?
The energy goes into the bearings, right?
Exactly.
So this was originally discussed through technical associates of South Carolina, North Carolina. Anyway, the technical associates first put that out in some papers like decades ago, right? And so we actually see it. We see the problems from that. We'll see the misalignment. We'll see the this and that. The other thing is people thinking, this is one of my favorites because we just did a set of tests at a plant where they had all belted applications, that you don't have to put shims or look for softfoot on the motor in a belted application. And I love that because we see softfoot. We see softfoot because when you tighten everything down,
Of course.
a static eccentricity, and that's a measurable loss.
Of course, you can literally distort the motor's case by bolting it to the ground.
Oh, you can't do that. It's cast iron.
Oh, get out of here.
Yeah, you can.
You know how much force an inclined plane, which is a bolt, can generate?
Oh, I know. I've seen it. I've also seen people put undersized shims under feet and bow a motor. You watch the bearings fail almost immediately, because when we go in, I just did this test on 53 motor. No, I'm sorry. That was the other location. That was something else. The other location, 10 machines. They just had us in for half a day. So we test 10 machines, and with RDI, they had seen softfoot, and it was very slight. Their alignment people said, "Oh, no, we're fine. We went in there, and guess what? We matched all everything that they found. We're like, okay, this one is half a kilowatt worth of misalignment, and another half a kilowatt or kilowatt in the bearings. Larger motor, about 200 horsepower, and so it doesn't sound like a lot, but so 1.5 kilowatts times 8,000 hours, that's 12,000 kilowatt hours, which means what 10 cents a kilowatt.
I was going to say 14. It's 14 here.
Yeah, so whatever it is, let's say 10 cents because that's easier to multiply.
Yeah, easy math.
That's $1,200 for not spending the extra few minutes to finish the alignment and or the shim. And then you couple that with so 12,000, that would be 12 megawatt hours, or 12 megawatt hours, and 12 megawatt hours times 0.709 comes out to be, we'll just round it to 8 metric tons of CO2. And a metric ton is heavier than an imperial ton, right? So it's 2,240 pounds. Yeah. So the it's like, so your guy who didn't do the precision alignment that you requested left you with softfoot. And by the way, that stress, that kilowatt we're measuring across the bearings, the only place that's going into is generating the defect in the bearing. You're feeding the forces generating the defects in the bearings. So they might last you a year or two, but it's going to be a defect. So
there's a compounding cost there.
Yeah. And something similar at another location, we found the same thing. It's pretty common. I mean, we're basically seeing things people don't normally see, including with vibration, right? They might say, oh yeah, there's a misalignment, but it's within tolerance. Well, tolerance is the minimum necessary. Doesn't mean it's good or great.
Right.
Same thing happens with electrical systems. We were in there and they're going, oh, well, the current says that the motor's not, at 100% load. And I'm measuring the kilowatts, and I'm going, well, actually, you're at 115 or 120 or 130% load. Well, how can that be? Well, you got really good power factors, so your current is reading lower. The nameplate says 0.85 power factor. That means that your current is that nameplate current at that power factor.
That's right.
The lack of knowledge of what's even in a nameplate is amazing.
Because power factor, I like to put it like in terms of like a beer, right?
Yeah.
When you fill
the foam
when you fill a beer up, you have your beer, and then you have your foam, right?
Yeah. I think I've used that meme.
Yeah, I mean, a lot. That's power factor is a really cool thing, and I'm not going to pretend like I fully understand its intricacies like you do, but it's an overlooked thing. A motor is doing its job under a rated state.
Yeah,
and these things have to be looked into. Power factor is one of them. And like, you can look at anybody out there and go look at a nameplate on any motor. You'll see PF power factor. It's going to be like 0.89 or 0.9 something, or a 1, which is a unity power factor, right?
Well, it goes beyond that. I won a court case using the empath some years ago, and because one of the measurements is power factor, and so the particular machine had been wound and the core had been damaged and all this other stuff so many times. Somebody literally had a chunk out of the steel, and they replaced that chunk of steel with epoxy. They shaped the epoxy as if it was steel. I mean, it was that bad. And we went in there, and it was like, we saw the unbalance of the power factor and certain other aspects I look for. And it's like, your core is bad in that motor. What do you mean? Well, your core is bad in that motor. That's why it keeps failing. And I just had the exact same situation near here. Somebody asked me to go in and take a look at a compressor. We went in, we found out, we discovered two things. With an electron surge tester, with their low voltage tests, we identified that that there was a problem in the connections in the motor, and found out that the end user had trimmed off some of the copper because the lugs they were put on the motor were too small.
Surface area, guys. Current needs surface area.
Yeah, it needs area.
Yeah.
And then the second part was, we go ahead and we test it. And I looked at the motor shop guy, and I'm like, you guys rewound a motor with a bad core. You know that, right?
Man,
it burned up 3 times.
That's a lot of work.
Well, why'd you do that? Well, it passed the test. Well, how did it pass the test? And when they sent me the data, I go, it didn't pass the test. Well, it passed the test. No, it didn't pass the test. It's just like, well, the resistive unbalance, it has to be 3%. You know where 3% came from, right? I put it into a standard many years ago, referencing back to my motor repair manual from the Navy. And that's how the industry got 3% impedance and 3% resistive unbalance. Yeah. Sorry, it was me. You sit on standards groups since 1993, some of the stuff we put in. So it was supposed to be a kind of a rule of thumb. It says, about 3% with certain exceptions and so on. Of course, everybody forgets that there's exceptions, and they don't look at the actual pattern, right? It's all pattern recognition. So I have 2 resistances that are identical, 1 resistance that's different, but it's only different by 2 1/3%. I'm sorry, it's unbalanced. You've got a loose connection in that higher resistance lead.
That's right.
And when you put it under, everything else, the impedance unbalance was higher though. It was like 4 or 5%. That was bad. So we saw that, and then we saw the power factor conditions and everything else inside the machine. So they had 2 problems. That's why they weren't able to solve it. It's one of the things I really enjoy about industry. I'll get called in, we can't figure out this problem, and you look at it and you go, oh, the reason why is because it's this problem, and oh, by the way, this and this are also a problem.
Sure.
And the weakest point is failing, so you're constantly addressing the one issue.
Sure.
But these other conditions still exist.
Yes.
You haven't broken all the chains of bad.
Yes. It's same thing as in my world too, Howard. Troubleshooting machines, you have an issue, right? But there's always the possibility of having subset of ancillary issues, right? That are compounding to create an issue. And you might see the big thing that says, hey, I'm jacked up.
Yep.
But below the thing that's jacked up is 4 other things.
Exactly.
And, I was in the shop working on a machine last night. I'm going to go to my shop again tonight and continue working on it. So it's having, it's throwing emission codes. And the code that comes up is a very general code.
Yep.
It says ATS fail, which is after treatment system failure. That could be a billion things.
Mm-hmm.
So what do I do, is just being the dumb guy that I am, I start at the very simplest things. I go make
keep it simple, stupid.
I go make sure that, do I have the correct voltage when the machine is running? Are any sensors getting a drop in ground or something stupid, right? Are all the connections tight? Oh my God, are the wires tight in the actual connections? Lo and behold, literally this whole code was generated by a loose connection.
Yep.
That's all. It took minutes to find. And it could have been so much more than that. And to your point is like people, they go after this like big thing. It's like, oh, this is the problem.
We ran into that with the 944
wheel loader,
John Deere. Yeah, the John Deere hybrid. I was one of the designers on the motor side, and I get a call, and they were talking about these issues they were running into, and I got to go over to John Deere once a quarter and teach the shop technicians about the machines, right? Because I was one of the last of the designers that was still around.
The dinosaurs.
Yeah, exactly. And we're only talking about 2010 or 12, right? I think it was finally released by 2015. And I said, did anybody check the grounds? And yeah, they're all mechanical folks, right? That's why they brought me in as a consultant. They need somebody who knew motor design.
Sure.
And somebody who understand the electrical components. So they had the drive guys, they had mechanical guys, and they had people like me for different parts. And they said, what do you mean? And I said, well, check and see. Well, sure enough, the problem was that people left a little bit of paint where they put that created a resistive issue.
Yes.
And because you're talking about electronics and everything else, it just
5 volts.
Yeah, pretty much. I mean, 5 volts. No, it's 700 volt machine.
Well, all the sensor, all the feedback,
all the references to the feedback for the but everything, including the motors, all had to be grounded to the frame. It's like a ship. 100%. I mean, any vehicle, it's an ungrounded system.
Yep.
You ground to the frame. So so even though they were AC systems, you still did all that stuff.
Right.
And it was something as simple as a little bit of paint on there.
That's so common, Howard. I mean, I work on machines constantly, and one of the biggest things that I get called for is electrical things.
Yeah.
And while I'm not what you are in the machine world, I know a lot about machine electrical issues, and I would say that 8 out of 10 times it's a poor connection or corrosion that is causing the issue. And it's just crazy to me that the fundamentals of Ohm's law, right? E over IR. I take that very seriously when I'm looking at machines and I'm troubleshooting. I understand when I'm taking a voltage reading, what a voltage drop means. I'm very, when I take resistive readings or I check continuity, I'm not going, does it beep or does it, I don't need, there's a lot you need to know. When I have I have an amp clamp, I measure current, so I'm trying, just like you and MotorDocs, like you have to get a holistic picture.
Well, and that's one of the things I'm enjoying about the technology too, ever since I started. I mean, I've probably been doing more research in grounds and neutrals than I've seen anybody do in a long time. I'm literally, the papers related to what I'm doing, I found 8 of them. That was it. Through the and the IEEE Explorer now goes back to 1935.
Wow.
Right. So papers that far back. And it's like,
they've got to be cool to read though.
Yeah. They are. Well, I mean, that thing where we talk about 51% of bearings, 10% of rotors and all that other stuff, that little pie chart that everybody shows, that's absolutely wrong, right?
I mean, I take a grain of salt with the majority of stuff I see nowadays.
Well, I mean, it started out, it made sense to me, and I kept seeing it, and it kept being repeated. Well, that's because nobody had the ability to get their hands on the papers associated with those studies. And everybody refers to the 1983 study that was solely done in coal-fired power plants. And nobody understood what they were looking at after just that chart was put out there, right? Because nobody had the actual data available. Well, all of a sudden, I think it was 2011, those papers were updated into IEEE Explorer. So I got my hands on the papers and discovered, well, one of the reasons why is, what's the first thing that happens when a motor goes in for repair? You replace the darn bearings, whether there's anything wrong with the machine or not.
Cut the commutator.
1/3 of the motors had nothing wrong with them. All the motors had the bearings replaced, and only a handful actually had any work done on them. So it skewed everything.
Right.
And it was basically based upon whatever report was returned to the utility, not the actual work that was performed, right? So 1/3 of the data was completely useless, and it was based on, I think, 500 or 600 repairs, or 1,200 repairs. So it wasn't a particularly large sample. But that study, 1983 by EPRI, 1985 published by IEEE, was an every 10-year study. So you can go back and see there was 1995 was the last time it was done. Then ESA did one later on. But 1995 was IEC motors, metric motors, on offshore platforms in the North Sea. The 1985 one was on utilities. The 1975 one was on commercial and industrial applications, which nobody ever quotes.
Wow.
That is more closely represent what happens in industry. Now, it kind of follows the other ones, but it's the exact same thing. What's the first thing you do with a bearing? Oh, you replace it.
Yeah.
So when you start looking at the details, the actual data, you start to find out that mechanical problems, yeah, they're a majority of the problems, but electrical problems are much larger than people think. And then everybody goes around, they do insulation to ground testing. And in reality, that's only 15% of the electrical based defects. It always starts as a turn short. So 85% of the time. So when we started into this, we just released in our last version of the software the ability to online measure the degradation in the insulation system.
Oh, cool.
Even on inverters, especially on inverters, because now we understand, and we did the research.
It's like a remote Megger.
Well, nobody included in any of their stuff the winding short signature, because in the 1990s, GE did research and published the winding short signature, and as well as Bill Thompson out of the UK, who developed current signature analysis. There's two different types, right? So Iris Power Engineering, or now Qualitrol, has a single phase current signature analysis only technology that they licensed from the guys overseas in the UK. The ESA, the one that the rest of us are using, are all based on Oak Ridges. But 1995, around there was a sudden publication. And what they had done is they twisted wires together and said, this is what the short looks like. So in our testing, we started noticing some patterns whenever we did motors on variable frequency drives. Started noticing this particular signature, and it was the winding short signature. Well, we had the ability to do it, but the software wouldn't automatically detect it. We had to actually go in and deliberately look for it. And we started discovering that it's actually what's called a winding stress signature. Now, I think it was either 2019 or 2020, I published it as an IEEE paper, the study we did. So we went to a Dow site, and we worked with them on a bunch of motors on VFDs. And we went around, we said, okay, we test this one. Hey, there's the signature. Yep, sure enough, the drive is not set correctly. Oh, the signature is not here. Sure enough, the drive is set correctly. Next one, not set correct. We started discovering that all the little partial discharges that destroy windings because you haven't set your drive up correctly, that, everybody, oh, it's a drive related failure, and ends it there, right? That's the root cause. They don't look as to why.
Sure. So
and we started fixing it all, and all of a sudden half their problems went away.
So do you think, like, I'm just thinking back to myself, like in places I've been and dealing with VFDs and things like that. Do you think a lot of people are not taking those drive parameters into consideration enough? Because when I think I think about it, it's just like the VFDs that I've had experience with, it's just like it's not plug and play, right? You just go through a menu and like, okay, nameplate,
Yeah.
and you're just putting in all these things, but there's still a lot of other things that
but
you don't
it's not just that. They aren't even putting in the nameplate stuff now. In the good old day, in the 1990s, when they first came out, they were so generic that you didn't have to put in a lot of information, right? And it would just put out volts per hertz. Then came open loop, closed loop vector systems and all this other stuff. I worked with the first, closed loop vector system, the Thor drive, that was invented by Wisconsin Energy and then licensed by a company called Thor, of course. So I learned a lot about it, and I had hired a technician that was a genius on those formula. I learned a lot from him. He's retired now, unfortunately, so the industry has lost that knowledge. But people don't realize things have become more complex. And to top it off, it becomes even more important because of all the additional systems we're putting in. I mean, that's been the study we've been working on, is not that, it's actually on ground and neutral harmonic issues. And so somebody will go up and they say, oh, there's only 2 amps on my ground, and they'll have a true RMS meter, and we'll go in with and grab a screen capture of an actual waveform, and it's like 20 amps to ground, but it's just messy as heck.
Right.
We took an argument back to IEEE on the IEEE 519, where they state something to the effect that fifth and seventh harmonic negate each other in grounds and neutrals. Therefore, it's not an issue. You only have to worry about third harmonic, called triplet harmonics, off of single phase systems. Well, that's not true. It's true on paper. It's true in textbooks. It's not true in application. We're seeing these higher harmonics, and they blow right through. Oh yeah, but we got power factor correction to fix things. Well, actually, your power factor correction is tuned for 60 hertz. All that other stuff feeds right through it, and then all of a sudden your power factor correction becomes a load. Everything. So we're going into plants and we're cleaning up their grounds and neutrals, and we're watching their energy consumption. I think the smallest one was 9.6%. And the most significant one was a plastics plant near here at 32.5% reduction in energy consumption.
It's just.
And then we went to another place, and they turned around and they said, well, can we get a rebate? And it's like, I talked to the utility. So the utility calls us up and they said, there is no way they had 26% on ground. I'm an electrical engineer with 1 million years of background and everything else. Well, here's the data. Use your own data. Don't take the bills, because the bills are usually averaged.
Sure.
You want to take the actual meter data. They took the actual meter data and the production information, did their version of data science like we did to match everything up with production. They came back and they were within 0.2% of what we were. So just 26%.
I know, it just goes to show
it's mind-boggling.
System design is so
back and forth on it because I couldn't believe it. It's like, this is not feasible. It's not possible. So I just published a paper, a peer-reviewed paper with NETA, National Electrical Testing Association, in the latest journal. It just came out in November 10th, on where all the losses are that contribute to this from harmonics on ground and neutral. It's not a secret. There's been work out there published on it, but I'm constantly getting into arguments with power engineers that were trained in the 1990s, and the 1990 training continues to this day, where we all thought, and we had done a study in 1995 with DOE showing that only about 2% opportunity from harmonics existed, including ground and neutral. Well, that was back before we had as many nonlinear loads, and we're, 5 going towards 7% of our total electrical generation goes to data centers, and things like that, where there's just this nastiness across the board. I've yet to go into a plant and go to a transformer and read right off of their power side and see something that looks sinusoidal.
Sinusoidal.
Yeah. The closest I get is usually some kind of thing with a flat top, which means high fifth and seventh, or notched all over the place, or it's got a slope on one side or the other, depending on the load.
I'm bringing the Navy back into this for a second.
Yeah,
it's so funny that you said sinusoidal. I took AC sine wave analysis in the Navy, and it was so cool. And that was this is the first time I've heard that word since then. What else is crazy too, Howard, is thinking about machines. I know we're way over time. We'll cut it off here shortly.
Right. You don't need to cut it out.
in machines, right? Mobile
Yeah.
machines, you will get the most goofy issues out of ground problems.
Oh yeah.
You will get, whether it's corrosion, loose, partially cut, whatever, you will get the goofiest like ghost codes, ghost issues, the goofiest issues. And ground is the suspect. Whenever I go into a troubleshooting process, and I like to call it strategy-based diagnostics, meaning like I'm actually thinking about what the problem could, potentials, as opposed to just pointing my finger and going, oh, I think that's it. There's actually, like, if you read troubleshooting documentation or you talk to people who do a lot of troubleshooting with machine electrical, there's always these identifiers that say, oh, I need to be looking at grounds. You know what I mean? There's this data, and I'm sure it's in your world too. It's like, I need to be looking at the grounds.
Exactly in my industry. And that's the problem, is nobody's looking. Oh yeah, this is something new. No. The fact that I look at grounds comes directly from when I took BEE in 1985. When I was working on my you'd have to do that before you can do the EM school, electrician's mate school.
Yeah.
So what did they teach us in BEE? Right away, it's check your ground, check your ground, check your ground. We're going to probably check your ground. That was Tesla. Tesla came up with that in the 1800s, late 1800s. Oh, and I'm sorry, even before that, Faraday even discussed
Faraday's law,
AC machines in 1826. So, it's like all these people are coming on and they're, oh, you don't know anything about this or ground, that's never a problem. It's like, well, then, I was on a sales call yesterday with Onyx, and I didn't realize I'd left my thing on, and this guy who had to espouse his background and as an electrical engineer and everything else, I started laughing at him. He did not appreciate it.
Sometimes they need that. But brings them down a little bit.
Like, and there's no way that, and this and that. It's like, no, it's not true. That's wrong. It's like having the argument about shunt. That I'm like, okay, it's a conductor, and there's roads attached to that conductor.
Yep.
You connect to one end of that connector, and you connect to the other end of the conductor. And he's trying to tell me that's not a shunt.
A shunt is a pathway.
It is a parallel pathway.
It's a parallel pathway.
And it's like, it runs in parallel. You don't know what you're talking about. I'm a PE. And it's like, good God, what state are you in? I want to avoid those PEs.
How are you bonding things?
Oh, California. That explains everything.
Yeah.
Sorry, everybody from California.
That's fine.
I'm going to continue to make fun of you guys. But actually, it's kind of bad because it's everywhere.
It is everywhere.
I mean, I jokingly said, after having a conversation with somebody and realizing that this guy with a master's in electrical engineering didn't know how to use a multimeter, I quipped about which university was from, and he goes, "How did you know?" And
that's the difference, man. Like I just had this conversation with Chris Pepin, and it's about application knowledge. You can't fake the work. You can have all the credentialing and everything in the world, but you can't fake the application work.
Yeah. And I'm always wary of anybody who calls themselves an expert. I mean, if you've read my stuff, I'm all about that. It's like somebody else has to determine you're an expert. If I was in the courtroom, they referred to me as an expert witness, but I would not be determined as an expert on electric motors, believe it or not, until the judge or jury or both attorneys determined that I was. So the first part of you being on the stand is them trying to throw you so they can say that you're not the other side.
Right.
Because they have to agree that you're an expert.
Right.
And, that's a true trial. I mean, I went into one, it was on ultrasound, and they go, "Have you ever designed an ultrasound meter?" Yeah. "Well, have you ever done this or that?" And then I finally got to one where I said no. So they came back, and then the judge had to sit there, and he goes, "Okay, but it's really obvious to me he's a global expert in reliability and maintenance." And this is before I got my CMRP, and I said, "Okay, I'm good with that." So the Sixth Circuit Court.
Yeah, there you go. Anointed you.
I'm a global expert. And it doesn't matter what your education is. You throw the education out there, that's the pre-qualifier. So in industry, how do you determine if somebody's an expert? Well, if people feel comfortable calling you and asking your advice and they follow through on it, I think that's a person that qualifies as an expert.
And it achieves a desirable outcome.
Yeah, and I'm gonna bend some noses and tweak some feelings here, but it's just like people running around calling themselves leaders. I'm sorry, that's not a self-determination. I don't care what course you took. I don't care what certificate you have.
You got to make other leaders.
How have you proven yourself a leader? And you might be a leader in an area, but you might not. I mean, I'm not a leader in a lot of areas. I keep getting thrown in leadership positions because people think I have a brain, and then they realize I fooled them.
Got them. Thanks for the money.
Yeah, exactly. But no, I tell you, the reason I work for myself is every company I've worked for, I get thrown right into a leadership position quickly. The last one, I was VP of engineering, and
well, you were in the Navy.
The company. Yeah, that's a big part of it. We learn the leadership you learn in the military is to look after your people, right? And now you see all these, I'm going to use the word woke, all this woke crap on things like LinkedIn about, a leader basically kisses the butts of the people that come after him. No, a leader is the person who has to make the tough decisions, has to know the people, and has to have the charisma to get the people to follow it, even if they know it's not in their interest.
Right.
But that the person they're working for is looking out for the best thing for the group.
And that comes from relationships and building trust and doing all the right things with the people.
Yeah, the decision being made is the best decision that person can make, and it's not self-serving and so on. I mean, that's kind of how I always looked at it. I mean, you always looked after your people. Every position I've had elsewhere, I've done the same thing. Even at SMRP, I looked after the staff. I protect, and by golly, I got them to get things done.
Right.
I pissed them off a lot.
Well, that happens. I piss a lot of people off too, because I'm extremely passionate, and I'm what you would call aggressive in a sense, not like physically or mean aggressive, but aggressive in my pursuit of excellence or change. Right. I wanted to touch one. God, we just keep going. I wanted to touch.
Well, I actually am going to have to get off. I've got a patent call.
Okay. Well, okay. So one more thing.
They'll wait
for everybody. Neutrals and grounds. Current has to flow.
Yes,
it has to flow.
Yeah,
it's not flowing into the abyss. It's going to ground.
To flow because there has to be a potential. That means there's going to be a difference.
And the ground or the neutral creates that potential, right?
Yeah, there's a voltage potential. There's an unbalance that allows current to flow.
That's right. And if your grounds or neutrals are jacked up, not bonded correctly, have paint, corrosion, trash, loose, all of that.
And everything's going to reference to that. So VFD will reference to that. It won't operate correctly. Electronics will reference that. It won't operate properly. I had a case where bearings and the windings were blowing up in motors, 300 horsepower motors. And it looked just like it was on a VFD that didn't protect itself. As a matter of fact,
across the bearings.
Across the bearings and everything. We found out that they had a ground loop condition in a high resistance grounding system. And on startup, they were seeing upwards of 180 amps on ground and 60 volts. I mean, if there was a loose connection on any part of that loop, any part of that ground, and somebody came in contact with anywhere in that path, they would have been dead.
You're welding at that point.
Yes. Oh yeah. And there were signs of that too. But the winding doesn't care. The insulation doesn't care. It just sees that potential, whether it's on the ground side or the winding side.
Right.
And so they would last 2 or 3 months, and then they'd have to be rewound.
It's just crazy. Everybody listening, follow the fundamentals. Use Ohm's law. Use your meter.
Mm-hmm.
Use your meter, and your oscilloscope. And if you don't know anymore, call MotorDoc.
That's exactly right. I mean, I don't know. I mean, people call me or email me. Email's probably best because I scan all my calls. Sorry.
All good, man.
I was just.
I know you got to go.
Late. I answer questions all the time. If it's not, I mean, it's literally, if it's something I can answer in about 5 minutes, I know that there's this whole thing about you're supposed to not answer the customer so you can bill more. I'm too damn busy for that. So, if I can answer a question in 5 minutes, I'll answer a question in 5 minutes. I do it on online forums like
creating value.
Yeah. And so on. If it takes more than that, then we'll talk about a project.
Right. Exactly.
But yeah, so
last thing, Howard, how do we get a hold of you?
Couple of ways. One would be through LinkedIn, which is the MotorDoc or Howard Penrose on LinkedIn. I don't use any other social media. You won't find me anywhere else. I got tired of the negativity and the poison and all that other stuff on there. And watching the nation's IQ drop or global IQ drop, I should say.
It's true.
Yeah,
it happens.
It's incredible. So you can reach me there. You can reach me at howard@motordoc.com. And it's MOTORDOC.com. And
like doctor, not doc as in a ship.
Yes. Or you can go to any of the websites. So motordocai.io, motordoc.com, and so on. So motordoc.ai.io is kind of a inside joke because I've developed some actual AI stuff that's out there that's working, but nice. It's hybrid. It's expert/AI.
Right.
And that's nobody had done that. I didn't realize that when we did it. Nobody else had done it. So I got a paper out on that in IEEE as well. And it was like, this is the first time, folks. We got into a knockout, drag down fight with the AI folks at AWS, thinking that they needed to modify something that I had created as an alert system for production for a pharmaceutical. And that they would need 20 years worth of data to replicate what I was doing on the first test.
You're outside my wheelhouse, man.
Yeah, it was just incredible. And disappointing too. I mean, we talk a good game, so do the marketing folks, but in reality, we're no different than we were when I used to teach this stuff in the 1990s.
Well, you're certainly still teaching it to this day. And anybody listening, there's a lot of nuggets in here. I could listen to Howard talk all day long.
And vice versa. I mean, come on.
I mean, he's been in my world in heavy industrial machinery. He does it now. I mean, it's just amazing. Howard, we're going to talk again. I'm so happy that you were able to join me. I'm glad we didn't have to cancel. And I'll be in touch. And anybody listening, please reach out to Howard and MotorDoc. You will not be disappointed. There's a reason why his name is on so many papers. His name is so recognized in not only industry, but in the government. I mean, everywhere that power is made, motors are turned, he's the guy. So Howard, thank you once again.
Thank you.
You are very welcome. And this has been UpKeep Pledge Pros Podcast with Howard Penrose, the MotorDoc. Please reach out to him and let us know if you have anything that you need from us. UpKeep is dedicated to unmatched value and unwavering support, and we'll keep getting after it. Howard, take it easy, brother.
You too, man.